Hi everyone, in this recording we'll be going over the determinant of a square matrix. Our goal is that by the end of this recording you'll be able to find the determinants of 2x2 matrices and other square matrices, and you'll be able to find minors and cofactors of square matrices. The definition of the determinant of a 2x2 matrix goes as follows. So A is a 2x2 matrix with the entries A1, B1, A2, B2. So the determinant of A is equal to A1 times B2 minus A2 times B1. Now the determinant of a 2x2 matrix gives us a lot of insight of how the matrix will work. So an example is the solution of a system of linear equations. So here we're given the system A1 times x plus B1 times y is equal to C1, and the other equation A2 times x plus B2 times y is equal to C2. Now we solve for x and y by isolating them. So x is equal to C1 times B2 minus C2 times B1 divided by A1 times B2 minus A2 times B1. Now y is equal to A1 times C2 minus A2 times C1 divided by A1 times B2 minus A2 times B1. Now we see that the denominators for both of the x and the y are the determinants of the coefficient matrix A. So that means our solution can be written in the form of C1 times B2 minus C2 times B1 divided by the determinant for x, and A1 times C2 minus A2 times C1 divided by the determinant for our y. We stated that the determinant of A is defined as A times D minus B times C, where A, D, B, and C are entries in the 2x2 matrix A. So if the determinant of A is equal to 0, that means that the matrix is singular. So A does not have an inverse. If the determinant of A is not equal to 0, then the matrix is invertible. So that means A has an inverse matrix. So the sign and value of the determinant can give us useful information about the matrix. So now we have some examples for computing the determinants. So for example 1, we're given the matrix A is equal to the 2x2 matrix with entries 4, 6, 2, and 4. So the determinant will be equal to 4 times 4 minus 6 times 2. So 16 minus 12 is equal to 4. So since that is non-zero, A has an inverse. Now for example 2, we're given the matrix B is equal to the 2x2 matrix with entries 4, 2, 8, and 4. So the determinant of B is equal to 4 times 4 minus 2 times 8. So 16 minus 16, and that is equal to 0. So there is no inverse for B. So B is singular. If A is a square matrix, then the minor Mij of the entry Aij is the determinant of the matrix obtained by deleting the ith row and the jth column of A. So in order to compute the minor of an entry, first we delete row I, then we delete column J, and then we can compute the determinant of the remaining submatrix. The cofactor Cij of the entry Aij is given by the following formula, where Cij is equal to negative 1 to the power of I plus j times the minor of an entry. So if the power I plus j is odd, then we'll have a negative sign, and if the power I plus j is even, then we will have a positive sign. So since the sign negative 1 to the I plus j is alternating, then it creates a checkerboard pattern of plus and minus signs. So here we're given an example where A is a 3x3 matrix. So I will go through finding a couple of the minors and the cofactors. So for M11, we are told to delete the row 1 from A and to delete the column J, so 1. Now we can compute the determinant of the remaining submatrix, so this portion right here, So then that'll be negative 1 times 1 minus 2 times 0, so that's equal to negative 1, and that's how we got this portion right here. Now for M12, we will delete row 1 and column 2, and now we can compute the determinant of the remaining submatrix. So 2 times 1 is equal to 2 minus 1 times 0, so that'll be 2, and that's how we got M12. Now for M13, so we will delete row 1 right here and column 3, and we can compute the determinant of the remaining submatrix. So it'll be 2 times 2, which is 4, minus 1 times negative 1, so that's negative 1. So 4 minus -1 is equal to +5. And that's how we got that right there. And now we just repeat the process for the rest of the minors. Now for the cofactors. So for C11, that'll be equal to -1 and 1 plus 1 for the I plus j. So squared, -1 squared, times M11, which was -1. So -1 squared is +1. So +1 times -1 will give us -1. And that's how we got C11 right here. Now we repeat the process, and that's how we get the other cofactors. So now finding the determinant of a square matrix, so now it doesn't have to be a 2 by 2 matrix, it can be any square matrix. This can be found by expanding along any row or column. So we need the cofactors in order to find the determinant. Now in order to simplify this process, we want to choose a row or column with the most zeros to reduce the work. So in order to find the determinant for any square matrix, we first compute the minors, then the cofactors, and then we use cofactor expansion to find the determinant. Now here are some examples going over how to find the minors and the cofactors. I'll go over the first one, and then you can use the second one as practice. So for example 1, we're given the 3 by 3 matrix A, and we're told to find M12 and C12. So for M12, we need to delete the first row and the second column, and now we're left with this matrix. Now we can compute the determinant. So 2 times 1 is equal to 2, and then -0 times 1, so that term will cancel. So we'll have 2. So the minor M12 is equal to 2. Now the cofactor given by this formula up here will be -1 to the I plus j. So I is 1 and j is 2, so -1 to the 3. So that means our term will be negative. So -1 times our cofactor, which was 2. Sorry, -1 times our minor, which was 2. So -1 times 2 will give us -2. So we'll have a cofactor of -2. So here's the key idea. A minor is the determinant after deleting one row and one column. A cofactor is the signed minor. Now once again, here's the 2 by 2 determinant rule. So if A is a 2 by 2 matrix with entries A, B, C, and D, then the determinant of A is A times D minus B times C. Now the determinant of a square matrix can be computed using cofactor expansion. So we compute the cofactors, well first computing the minors, then the cofactors, then we can expand either using the rows or the columns. Now we want to choose a row or column with the most zeros so that those 0 entries will contribute 0 times their cofactors. That just means that those terms will vanish since 0 times any number is 0. Now we can expand along any row or column and we will get the same determinant. Now some of the key ideas to remember about determinants is that if the determinant of a matrix A is equal to 0, then that means that the matrix is singular. So that means it is not invertible and we cannot find an inverse matrix of A. Now if the determinant of A is not equal to 0, then the matrix is invertible and we can find an inverse. So now we're given some examples to work through to find the determinant of square matrices. I'll go through example 1 and then you can go through example 2. So first we want to expand along row 1. So that means we will use the coefficients or the entries from row 1. So 2 times C11 plus 0 times C12 and 1 times C13, so that the C12 term will cancel out and we just have to find C11 and C13. In order to find C11, we need to find M11. So that means we need to delete the first row and the first column. And then we find the determinant of the submatrix. So 3 times 0 minus 1 times 2 gives us -2. Plugging that into our cofactor formula, we get C11 is equal to -2. Now for M13, we delete row 1 and column 3, and we find the determinant of the remaining submatrix. So -1 times 1 is -1, minus 4 times 3 is equal to 12. So -1 minus 12 is -13. Plugging that in to our cofactor formula, C13 is equal to -13. So now, using our formula for the row expansion, we'll do 2 times C11, and C11 was right here. So 2 times -2 plus our 1 from the last entry times C13, which was -13, and that'll give us a determinant of -17.